Dear colleagues, my name is Irina Sotnik. I'm a professor of the Department of Economics, Entrepreneurship, and Business Administration at Sumy State University and a research collaborator at the University of Geneva at Renewable Energy Systems Group. I would like to present to you my job market paper titled Decarbonizing Ukraine's Electricity Sector in 2035 Scenario Analysis, which was written in co-authorship with my Swiss colleagues and published in Energy in the journal Energy and Climate Change in 2025. To start with, let's consider the relevance of this research. As a member of the European Energy Community and contributed to the Paris Agreement, Ukraine is obliged to reach carbon neutrality by 2050. The war in Ukraine questions the feasibility of earlier developed energy system models and strategies and requires updated solutions for rebuilding the electricity sector in the post-war period. Besides, decarbonization, issues of regional decentralization of energy capacities become urgent and strategically significant. Based on the conducted literature review, we found out that the previous publications considering model of Ukraine's energy sector mostly use the macro model times Ukraine and others, which does not reflect the regional infrastructure of the United Energy System of Ukraine and therefore does not optimize electricity generation, storage, and transmission in the spatial context according to decarbonization targets. This lack was addressed in our research by applying the spatially explicit bottom-up single-year optimization Ukraine expanse model, allowing cost-optimal regional distribution of different generation, storage, and transmission technologies, and assessments of their social, economic, and environmental impacts for Ukraine in 2035. Therefore, the aim of our research was to offer cost-optimal scenarios for developing the United Energy System of Ukraine in 2035 using different constraints on the applied electricity technologies available in the market and contributing to the national decarbonization targets. This slide presents the structure of the Ukraine expanse model, which covers 5 neighboring countries like Poland, Slovakia, Hungary, Romania, and Moldova, presented as single country nodes, and 24 Ukraine's administrative regions, excluding the territories of Luhansk and Donetsk regions occupied by Russia before 2022, due to unreliable statistic, and of course Crimea, due to the same reasons. The next slide presents the list of technologies used for modeling. It includes 17 generation technologies, the most widespread today, including the traditional one like electricity capacities on hard coal, nuclear power plants, hydropower, as well as other renewable energy sources like onshore and offshore wind power, solar PV, biogas, agricultural municipal waste, and others. Also, we considered 3 storage technologies, including pumped hydropower storage, power to hydrogen, and batteries, and 2 transmission technologies. For our model, we used alternative current for Ukraine's domestic lines and direct current for neighboring countries. The next slide presents the main assumptions that we used in our model, namely the degree of electricity infrastructure destruction depending on the proximity of Ukrainian regions to the front lines and depending on if there are hostilities in these regions. And this table exactly presents you the differentiation of destruction depending on different regions. Of course, the highest level of destruction we assumed for Donetsk, Luhansk, and Kharkiv regions, which exactly on the front line and partially occupied by Russia. Then the lower levels of construction, but still very significant, like 70%, we assumed for Zaporizhia, Kherson, Kiev, and Mykolaiv, which experienced the most pressure from Russian attacks. And other regions like Chernigiv, Sumy, Dnipropetrovsk, and Odessa, we assumed 50%, and for other central and Western oblasts, we assumed the lowest percentage, like 30 and 20%. I just want to remind you that this differentiation was assumed as of May 2024. Of course, for now, situation has changed. The next slide shows the main constraints and scenarios of our research. So we developed four main scenarios. The first one, mean cost, assumed no constraints, just cost optimal. Then we introduce the first constraint on ceasing hard coal by 2035, and therefore we have scenario coal zero with coal zero constraint. The next constraint includes the 30% of renewables in the electricity mix. And we called it RES 30%, and the corresponding scenario we also named as RES 30%. The combination of two constraints, like hard coal, season hard coal, and increasing the share of renewables up to 30%, form the fourth scenario, coal zero plus RES 30%. As for the next constraint, we assumed the annual greenhouse gas emissions corresponding to the contribution of Ukraine to the Paris Agreement. So it means that the CO2 emissions by 2035 should be less than or equal 29.7 megatons of CO2. And it was found out that these constraints have been satisfied for all scenarios. So we just keep it like satisfied by default. The next slide presents the distribution, the structure of installed electricity capacities by developed scenarios in comparison to the previous structure of capacities and the current one, undamaged as of May 2022. So you can clearly see that based on all scenarios, in 2035, Ukraine will use a lot of nuclear installed electricity installed capacities in orange, then wind capacities in dark blue and light blue. This is the onshore and offshore wind capacities, also solar capacities in yellow, dark green for hydropower capacities, violet for hydropower, pumped hydropower storage, green, light green and a bit darker green, it's for municipal waste, agricultural waste and biogas, and the gray for coal. So you can see that if we don't apply the coal zero constraint, then the main sources for the main structure of the main technologies in the structure of installed electricity capacities will be nuclear, coal, and wind. The next slide presents the distribution of electricity generation. And again, we can see that the highest shares of electricity generation is from nuclear power, with the help of nuclear power plants. Also for scenarios with coal zero constraint, the hard coal will be replaced a bit with bioenergy, so agricultural waste and biogas. And still the share of wind power will be quite significant, as well as the share of solar and offshore wind, like also for gas in red, will be a bit lower. Also, you can see here on this slide the volumes of import and export flows. Export in yellow, light yellow, and import in dark blue at the top. And you can see that actually the yellow, so export, is higher than the import. Okay, this scenario presents the social, economic, and environmental effects of scenarios. So in terms of environmental effects, we calculated the CO2 emissions volumes in 2035, and it turns out that the MINCOS scenario and S30% scenario provided the highest emissions. However, within the level of decarbonization constraints. And the lowest one were provided for scenarios with coal zero constraint. As for air pollution, the lowest one in terms of PM10 emissions, the lowest volumes of pollution was provided in the MINCOS scenario, while other scenarios gave quite higher volumes of air pollutions. As for social effects, in terms of direct electricity sector jobs, the highest levels of jobs were provided by scenarios with coal zero constraints, while the minimum among scenarios, number of electricity sector job was found for the MINCOS scenario. And as for direct land use, again, the minimum land area was required for MINCOS scenario and the highest one for scenarios with coal zero constraints. This slide presents the economic effect scenario in terms of total system costs in billion euros per year, and we can see that the highest levels of expenditures for the system, for the electricity system functioning, is provided by scenarios with coal zero constraints, while, of course, the minimum is occurred for the MINCOS scenario in like 10.4, and the highest value was 11.7 billion euros per year. So going to the modeling outcomes, I should say that despite a 16.3% of electricity demand increase by 2035, it would be possible and feasible, according to these scenarios, to reduce the total installed electricity capacity in the country by 5 up to 20% compared to the previous period due to the rationalization of developing and using diversified energy technologies in the regions. Also, compared to the undamaged electricity facilities as of May 2024, the growth of capacities until 2035 will be 2.7, 3.2 times, and will occur primarily in the eastern and northern regions, most affected by war. Again, all scenarios allow reaching decarbonization targets, and the policy focused on cost efficiency in terms of mean cost option will preserve the high nuclear power share in electricity generation, while utilizing some of the remaining undestroyed hard coal facilities. In addition, nuclear and gas power will still remain the primary fossil fuel sources for electricity in 2035 in all scenarios, supported by intensive growth in wind power, pumped hydropower storage, bioenergy, and expansion of transmission grids. And as before the war, Ukraine will remain an electricity exporter, having increased its export capacity. And to sum up, implementing environmentally friendly scenarios with coal zero constraints in particular will require additional costs, starting from plus 5% up to 13% more compared to the mean cost option, and are socially acceptable. Of course, the main limitation of this study is the initial data, because now, in terms of our research, the electricity data was closed to the public due to the security reasons. And of course, it forced us to make assumptions, which may not reflect the reality. And because of this, of course, we cannot say that the scenarios are 100% real. However, the discussion that we conducted in this research confirmed the obtained results with the achievements and the results of other papers. That's all about this job market paper. Thank you for attention, and bye.